Yeah, we be talking about the ancient mariners and navigating the high seas in today's lecture. We are going to be looking at all that we know about the Earth so far and observing a little of what other swashbucklers found out as they traveled the high seas. Ah! The other name for this lecture is Holy Boop, Where Am I? Because trying to find your way on a sphere is not 100% easy. So, to help us understand that, we're going to first introduce a couple of terms that are commonly used in navigation. So, first thing I always like to point out is that Earth is, of course, a sphere. If we have to have a conversation about flat Earth and people keep pushing that out there, I'm not sure if this is the class where you're going to learn what you need to learn this semester. So there we go. Earth is a sphere, roughly. Technically speaking, because Earth rotates, it bulges out a little bit the equator, so technically it's an oblate spheroid, but we're not going to worry too much about that. We're going to use a model in which Earth is a sphere, and we'll find that this model works really nicely for explaining the basics of maritime navigation. A little about what we're covering today. We're going to cover navigation primarily. We're going to first focus on latitude and longitude. Then we're going to focus on how different observations of the Earth system, that will be pretty much most of what we do. And we're going to be focusing on, and honestly, there's a lot more things out there than I can fully cover in this class, but this will hopefully at least serve as a taste of sort of what is possible. So the first term I'm going to introduce today is latitude. And so the trick to this is, when you're navigating on a sphere, generally what people try to do is they take a map of the world and they try to take a spherical object and then try to flatten it, because it's a lot easier to fold and carry a flat map than it is to carry around a sphere. Now, for example, your screens are probably closer to flat than they are closer to spherical. So when you're moving around a sphere, any journey around that sphere ultimately will be a circular line. So we need to find some way to create a coordinate system that'll help us sort of understand the circular lines of our planet. So it's also useful probably to think about, you've probably noticed this with the stars, that we are on a planet that is rotating about a pole of rotation, so that if you were to stick a pole pretty much to the Earth, it would rotate fairly evenly around that pole. So first thing we're going to introduce is, so at some point, the widest portion of the Earth, the point furthest from that pole of rotation on the Earth's surface, is known as the equator. So on a planet, we have a pole of rotation running through it. And where this pole of rotation pierces the Earth, you have the North Pole. And of course, if there's a North Pole, there has to be a South Pole. Well, and then we have this rotation taking place around this pole. So meanwhile, we have this equator. This is an imaginary line which is equidistant between the two poles of Earth. So we can think of our location. So one way to think about our location is where we are relative to the equator and the poles. So if the pole is a point and the equator is a large circular line circling the world, then you can imagine a bunch of smaller circles all that to be parallel to both this circle around the widest part of the planet and widest part of rotation and a point. You can construct a series of smaller and smaller circles. And then at any point along any of these circles, whether you're close to the North Pole or close to the South Pole, you can imagine some point at the center of the Earth. So what you can do is, once you have a center of the Earth, then you can draw an imaginary line in the center of the Earth and the equator. And then a second imaginary line between any of these other lines on these other parallel circles on the Earth's surface. And then the angle between these two lines, it would be the latitude. So latitude is an angle, and so we measure angles. Most of you are probably familiar with degrees. North Pole would be at 90 degrees north, and the South Pole would be at 90 degrees south. So you can see that this angle between the equator and this pole here of rotation where it comes to the surface will always be, at the equator, will always be 90 degrees south. So between the equator and each of the poles is 90 degrees. And so if you think about it, this makes sense because then you're going to go back down here, and if you're at up 90 degrees from the equator to the pole, 90 degrees from the pole back to the equator, and then 90 degrees from the equator to the other pole, and then 90 degrees from the pole to the other equator, that would add up to 360. So we also call lines of latitude parallels. So for example, in North County, you are probably very close to the between the 32nd and 33rd parallel. So you are just about a third of the way between the equator and the pole here in San Diego County. So degrees are kind of the typical unit by which angles are measured. Of latitude, 1 degree of latitude is roughly equal to about 111.11 kilometers. This is because when the French made the metric system, they said that they designed the unit, the meter, for there to be 10,000 kilometers between the equator and the North Pole. So if you're ever stranded on a desert island and just trying to figure out how far away things are based on latitude and longitude, that is a very useful tool. Now you're going to see it's not going to work quite as easily for what we're going to discuss next. You're also going to see we break this up into a couple smaller units. We have a pole of rotation. The distance between sort of the furthest point from that pole, those poles of rotation, angularly, is fairly easy to determine. However, you need, when you're dealing with any surface, even if that surface is spherical, you're going to need at least 2 sets of coordinates. This is where life gets a little interesting. So we're going to use a different color for this because here. So when you're doing longitude, you could draw circles like this, but that would be a hot mess and be very confusing. So instead, what we did is we still draw circular lines around the world to measure angular distance east-west, but because we're on a rotating body, we have all the lines measuring east-west angular distance converge at the poles. Then we call these lines of longitude. Now, the thing about when you're on a rotating body, while you definitely have fixed points at the poles, you don't have any fixed point with respect to the east-west direction. So determining 0 in this system is a little bit more arbitrary. So we define longitude as angular distance into / opposite the direction of rotation. And we call lines of longitude are called meridians. And they are generally not parallel. Not parallel like your lines of latitude. In fact, if you wanted to measure distance longitudinally, it's going to be a little bit more complex. So 1 degree of longitude is going to equal 111.111 times the cosine of your latitude. Is longitude in kilometers. 111 times the cosine of your latitude. And that will give you a rough idea of what 1 degree of longitude is. So if your latitude is 0, yes, it'd still be about 111.11 kilometers. But if you're close to the pole, 1 degree of longitude is going to be absolutely nothing. I have friends who have been to the pole. It's pretty awesome. The South Pole. So now we want to break up our units of angular measurement into smaller units because clearly 111 kilometers is a fairly large number. So within every degree, we break up our degrees into minutes. We have 60 minutes per degree. That's going to give you something that's about a mile or about a kilometer in length. And we'd still like to get something a little more precise for figuring out where we are. So for every minute, we have 60 seconds. So with the degrees, minutes, seconds, you can pretty much locate yourself to within a few tens of meters, just using whole numbers. You may wonder, why do we use base 60 for this? Well, there's a lot more numbers that go into 60 than go into 10 or 100. And so it was much easier to use set units before the onset of calculators. So a couple other things to remember about longitude is that we do have to have, however, a standard reference point. So there are two standard reference meridians. The first reference meridian is the prime meridian. This runs through basically Greenwich, England. Greenwich, England, UK. It actually runs fairly close to Paris, France, and it runs through Western Africa. The reason this is used is entirely an artifact of colonialism and the fact that when this system was being standardized, England was a maritime superpower of its day. Now, this is going to be the 0 degrees east and west. And all lines of measurement are measured relative to Greenwich. Now, of course, you need to have a second sort of standard point. We call that at 100. We call that the anti-meridian. This is 180 degrees east/west, and it runs roughly through the Pacific Ocean. Actually, cuts through the easternmost tip of Russia, and indeed Russia, and cuts through a bit of Antarctica, but otherwise manages to not cut across too much in the way of land, except I think one island out in the middle of the Pacific Ocean. Intriguingly enough, I had to deal with the anti-meridian quite a bit in my work because the area in Antarctica I was looking at it crossed right through there. And so we had to invent a completely different coordinate system to deal with the fact that you're going from 180 and then going down.